we're 1 minute past 1:35. I think we'll get started. So are there any questions on the homework? Are there any things people want to bring up before we get started on slides today? I fielded a couple questions on homework and the right paper and what people need to be working on over the weekend. But if you want to unmute yourself and say anything, now's the time. All right. Well, it sounds like everyone is getting settled on finding a good composites paper and working on their write-up. So I'll look for those. And you should have your homework 3 graded. And so if something gets off track, just let me know because I know things come up. But anyway, let's switch over to slides here as soon as I figure out how to share my screen. If I can get to PowerPoint, there we go. All right, so we're still talking about SLS, and I think either we're going to finish up today or we're going to finish up next week on selective layers sintering, and then we're going to talk about some other sintering technologies as well. But I wanted to keep going talking about powders, how SLS fits into the overall scheme of additive manufacturing of polymers and composites, and then talking a little bit more about composite powders, even though there's not a whole lot out there yet. But some good questions were brought up last time on, why should we do this anyway? And so I will continue to build that case up in terms of why should you additively manufacture parts? Why should you use SLS versus SLA versus FDM? And there's a lot of interesting questions in selecting the right material, the right manufacturing method to get the requirements or to meet the requirements of whatever component that you're building. And so we'll continue to build that up as we go along. But if you ever have any questions on why is this important? Is this a research activity? Is this production? Where is this used? What industries is this technology important to? Please pipe up and ask those questions. Those are good things to round out our knowledge of 3D printing and additive manufacturing. So any questions here to start off on the slides or any follow-up questions? All right, so we're still on lecture set 6.1 and we're going to jump back and forth a little bit here. But as I said before, there's not a lot of composite powders out there in the marketplace. This is usually a research activity. We'll talk about some composite type parts that are built using SLS, but for the most part, we're looking at components that are pure materials. They're things like this turbine blade mock-up assembly, or this cutaway of a turbine engine, or you've seen the skull implant before. But a lot of SLS parts, are single materials. But in some cases, there's room for using composite powders or using powders that contain 2 different components to try and increase the mechanical strength of the polymer, or to change the electrical properties, or to give the composite some other feature that you can't get with just pure polymer. And so in this case, you have a polymer powder, and this is what does the sintering in this case. So this is active in SLS, and the silicon carbide is just a filler. And so I'd have to look at this paper to see if they were looking at mechanical properties, or if they were looking at the RF properties or something like that. But every time you make a composite powder, it's really important to think about this idea of what's the particle size distribution? How do the particles fit together? What is the SLS performance going to be? And so, in these SEMs, it's hard to see exactly what's going on in terms of what the powder looks like, but these are all considerations that you need to take into account when you're interested in doing sort of composite SLS. And it's really, at this point, there's composite powders where both components are powders. You don't really see a lot of chopped fiber. You certainly don't see continuous fiber. You don't see some of the stuff that we saw in composite material extrusion AM, where we were looking at whiskers or something like that. And so this is pretty much the state of the art of composites and SLS, which means there's not a lot going on yet, but this is of interest. One of the things that I want to bring to your attention when you see some of these powders, and so if you just look up, this is just one material supplier website, powders for SLS, oftentimes the powders will be dark or gray, and there's no white powders in this. And these darkening agents, so these colorants or darkening agents, are used to tune light absorption and heating. And so oftentimes you'll see some gray powders, or you may see some gray parts coming out of SLS. So even though in this case in the EOS machines, those are generally white PA12. Of course, PEAK is naturally brown, so it has good light absorption. But this is for this type of machine. So Sinter it is a small scale lab SLS. So it generally has a lower power laser so it needs darker powder for heating. And the way that powder is darkened is that they just add carbon black or graphite particles or some cheap dark particles to the polymer in order to darken it so you get effective sintering. So these powders, in essence, are composite powders of carbon plus polymer. So don't be confused when you see, oh, this part is PA11, it's nice and white, and then they're selling these other powders that are PA11 or PA12 or TPE or something like that, and they're gray. They're just have a darkening agent in there, and the darkening agent doesn't necessarily change the mechanical properties of the material per se, but it changes the absorption of the laser, especially in different machines where you don't necessarily have high power lasers that you can get good sintering of white powders in. So that's just a heads up on if you're going out and buying SLS powders, what to look for, or another tweak if you're designing SLS powders, you can modify the light absorption by making a composite powder. So that's something to remember. We're going to switch over to a different set of slides. So if you go to Box, before we finish up these last slides on this, if you go over to Box, there should be a set of slides called 6.2. And so you can go ahead and bring those up and follow along in the lecture, take your own notes, etc. But they're in Box for you. If for some reason you can't find them, just let me know. But there's a lot of interesting stuff for polymer powders out there. And like we discussed before, metal powders have been around for a long time because of MIM, or metal injection molding. But polymer powders have not been used in this way other than through the advent of SLS. Now, polymer powders have been made for compression molding and some other polymer processing for a while, but those powders were not as sophisticated as what's required for SLS. So I think it's worthwhile to look at polymer powder feedstocks and look at some of the phenomena that happen with these polymer powders and SLS to continue to build up our knowledge base in this area. So there's this nice article right here. It's short, so I suggest you take a look at it. But this article talks about some of the requirements for polymer powders as we're thinking about deploying new powders in SLS. And so we've talked about powder particle shape and size distribution so far. We've touched on optical properties, and of course the optical properties are coupled to the laser light to thermal thermal heating. So that's an important property that can be tuned depending on what the polymer powder is. Surface tension is important to fuse polymer particles together. And then they have this really interesting paragraph on zero shear viscosity, and they show an example of that in figure 5 in this paper right here. So these are both polyamide 12 parts. One of them has a low zero shear viscosity, so eta 0 is the zero shear viscosity, and a low zero shear viscosity means that it flows easier when subject to melting. So this one flows easier, or let's say flows more readily. Where if you have a high zero shear viscosity, of course, this is going to have a higher flow modulus, and so this doesn't sinter as easily. And you can see that because you have optical defects. So these are either holes or unsintered particles. You don't really get good coalescence of the material if you have a high viscosity, because of course it doesn't flow as well. Where here you have very uniform coalescence of the particles because the viscosity is lower. So as you're sintering these things, you get good coalescence within your part, and the part looks good. Because of course, any of these optical defects have the chance to become a stress concentration defect or some other defect that changes the properties of the part. So these are some important things to remember as you start to design or select a polymer feedstock for your polymer powder in SLS. Now, one issue with this is that there's lots of different things going on in terms of the crystallization and the speed of processing. So this paper right here is where this SLS sintering window is from. And remember, this is in differential scanning calorimetry, and the heating rate in DSC, at least for this one, is 10 degrees C per minute heating and cooling. But we know from SLS, you have tremendously high heating and cooling rates. So in SLS, you have much higher heating and cooling rates, such that this type of sintering window only gives you a guide as to what might happen in terms of what you can expect when you're doing tens of degrees a millisecond in SLS. And so this is figure 2 right here. So it says the scheme in figure 2 is an idealized representation of the thermal properties of this polymer. And so this is the issue where, you know, the measurement that you're making analytically in DSC is somewhat representative of what you could expect from the material, but when you're processing it, things are happening much faster. And we know that processing speed can have an influence on polymer properties. And so they talk about, you know, this DSC is at 10 degrees C per minute, but this never occurs during SLS. And so, you know, the sintering temperature or the processing temperature during sintering is going to be very close to the crystallization. And so that means that the crystallization is going to shift to higher temperatures for SLS processing and be more in this region. So you really want to be close to that melting. And of course, in SLS, you don't get to control the temperature precisely. And so, you know, even though this is still an idealized schematic, lots of things can be happening in terms of what's happening in SLS, how the laser is controlled, and that's why you have to optimize the scan speed, the laser power, all of those things, whereas this SLS or this DSC just gives you a guide as to what's going on. So there's lots of words here, and so this, you can read this if you want, but basically they're describing some of the considerations that you need in order to think about what's going on in a semicrystalline polymer. So of course this is for semicrystalline polymers with low zero shear viscosities. So this gives you an idea of things to look for. So for amorphous polymers, there's no TM or TC, and they tend to have higher zero shear viscosities, even at high temps. Which makes particle coalescence difficult, which means you have poor sintering behavior of amorphous powder. So having a high zero shear viscosity makes particle coalescence difficult. And so that's one of the reasons why we don't have a lot of examples of amorphous polymers being used in SLS, because it's hard to get those particles to sinter compared to semicrystalline polymers that tend to have lower zero shear viscosities near their melting point. So that's sort of a compare and contrast about why this sintering diagram is important and what might happen at faster scan rates. One cool thing that they show in this paper is that if you have, if you're sintering, so this is again TC and TM, and your sintering temperature is moving around between here and here. So if you're in the SLS region and you just change the part bed temperature by 5 degrees, in one case you can have curling. So this is premature crystallization. Whereas this is lateral sintering growth. And so you lose XY resolution if you're getting too much thermal diffusion. And if you're getting premature crystallization, that means you're too close to TC. And so you're getting crystals or a densification, let's say. And curling. So anytime you see this curling / warping, it's usually because you have some sort of densification process or too much of a thermal gradient, and you can see that that part curls up, and that's very bad news when you start to think about the operation of a powder bed and spreading powder over that curled part. And so this is where optimization of the bed temperature and the laser power really comes into importance, is you have to balance these different factors in order to get the resolution you want, and you don't get over melting versus curling of the part or some sort of unsuccessful build. So again, this sort of lays out the basic framework for how to think about these problems, but of course, depending on exactly the machine you have and exactly the powder you have and the thermal conditions in the instrument, it's going to take some optimization to nail down all these different factors. Any questions on this? So I know that this is sort of speaking in terms of, you know, what theory is like, and it depends on exact conditions, but hopefully this gives you something to look out for if you go deeper into SLS or think more deeply about polymer powders. These are some of the factors that you're going to have to think about as you start to work on these processes. Another really interesting facet of this is we talked about powder morphology last time or the time before, and what the particles look like themselves and what the size distribution is. And one of the ways that they look at these sorts of powder flowability issues, so this is you need to spread powder evenly during during SLS layer build. That gets to this term of powder flowability or powder rheology. And they use this cool parameter called the Hausner ratio. And all it is what is the bulk density of the loose powder. So if you just take powder and measure its volume and mass, you can get a powder density versus this parameter called a tap density. And all the tap density is you basically take a cylinder of a certain height and you tap it a certain number of times and you get this tap density. And so this Hausner ratio, a Hausner ratio of greater than 1.4 means that you're going to have fluidization problems or the powder really likes to stick together, versus if you have a Hausner ratio of less than 1.25, you have this nice free-flowing powder behavior. So that tells you about how well these polymer particles stick together, because of course tap density is in the numerator versus just your bulk or your loose powder density. So these are just empirical. 1.25 and 1.4 are empirical observations. But if you ever come across literature in polymer powders that's talking about the tap density or what the bulk density of the powder is versus, of course, the density of the polymer, which is usually based on a solid sample, these are some of the parameters that you want to be aware of. And so, of course, to do a proper powder flowability study, you'd like to do the powder rheology in a rotating drum, or to do some powder spreading studies where you're actually looking at the spreading of the powder in the SLS instrument or in the some sort of powder spreading experiment to make sure you can get the right layers and the right layer heights and everything else with no defects. But this is an interesting observation. Any questions on this so far? All right. So there's lots of interesting papers, or there's a number of interesting papers out there about how to produce powders, especially how to produce experimental powders. And so if you look on some of these websites, there's lots of filaments available. There's lots of ways to find filaments. You can get filaments made by extrusion. There's lots of feedstocks for SLA. There's lots of feedstocks for other types of 3D printing processes, but there aren't many feedstocks available for SLS. And so trying to figure out the most productive way or the easiest route to SLS feedstocks is an area of interest. And so this is one example of a paper here. And so this is adapted from a figure that we've seen before, where it really matters what the individual particles look like and how they were made versus powder size distribution. So that goes into the density and the flowability, as we just discussed. And then you have all the instrument parameters down here, where you can go from a polymer feedstock all the way to a laser sintering powder and what it's going to take to SLS that feedstock. So this paper walks you through the process of making this blend first off. So they're melt blending two immiscible materials, and then they make some sort of feedstock. So this is the blended feedstock. And then they do some rinsing of the feedstock, and they do some particle sorting to get the right size distribution. They dry the feedstock, and then they're ready to go for some sieving. and then they're ready to go to SLS. So making polymer powders like this is a multi-step process, and this paper discusses some of the things that they do. These are the sintering conditions that they used in their process, and I can't remember exactly what instrument or what machine they used to do their SLS, but this gives you an idea now of all the different things that can be controlled in this SLS process. So you have a bed temperature. So that's the static temperature of the refrigerator, or at least the bed temperature where you're going to shine the laser on. And so this is above TG, because remember, the laser is just going to bring you up to that sintering temperature, and then you're going to stay above the glass transition temperature of the polymer to get effective sintering. In this machine, they can control the piston temperature. So that's sort of like the build plate. What is that temperature? They can control the cylinder temperature, powder feed temperature, laser power, scan speed, and then all the hatch distance is side to side. How far is the laser away from one another, layer thickness, etc. And then they can finally get an energy density out of that. So that's all very interesting because these are the things that you have to control as you go into your powder bed process. And these are some of the things, depending on what machine you have, you want to take into account to get effective sintering. And so they show some interesting examples right here. So this is a pretty good build. So you see the sintered SLS parts in a nice smooth powder bed. In one of their trials, they were getting curling. And the powder recoater was actually moving the parts around on the powder bed, so that's not very good. And that will stop your build in a hurry. And so this paper sort of walks through how they did the optimization, how they optimized conditions, and then they report for SLS versus IM is injection molding. And remember, this is extrusion mixing. Just like a conventional polymer process where you have lots of mixing, you've got lots of shear, everything is very well incorporated, and you get a good consolidated polymer part. CM is compression molding. And that's done by compressing powder. And so if we look at the mechanical properties, the Young's modulus is pretty good, right, for all of these. It's on the order of, compression molding's a little bit lower, but let's say on the order of 1900 to 2200 megapascal. That's not too bad. However, the elongation to break is a real issue, including the maximum strain, the maximum stress at failure. When you process from powder, you're not able to elongate the sample as well. It's a little bit porous. And so all of these values are because of particle consolidation or porosity leads to low strength or lower strength at failure and lower elongation at break versus injection molding. And so as we discussed last time, this is the real flaw of SLS is trying to get all that powder to stick together without any defects usually the parts have reasonable moduli values, but their strength at failure and their elongation at break are lower because of the consolidation of the powder. So that's something to think about as you think about how to use these processes. The other thing that happens, and this is a really cool image, is that as you build this part, so in the initial stage of SLS, so this is layer 1, and this is layer X, whatever it is. So you're building up this way, just as the arrow says. In the initial stages, you're getting a nice dense microstructure. You have some flaws, but not too many. But as you start to make the part thicker and thicker and thicker, because you're getting warpage, you have this delamination defect. So in essence, what's happening is as you're coalescing this powder, the part is starting to warp, and then the machine is getting out of register in relation to where the part is, and you start to get this partial coalescence. And so as these parts, let's go back to the image, as these parts are moving around on the powder bed, or as you're getting more and more coalescence, you can get different sorts of defects as you make the structure thicker and thicker and thicker. And so this is something that has to be examined, and this is something that you have to think about it when you set up your build profile, is if you get too much coalescence at the bottom down here, you can get really significant delamination issues later on in the build as you build the part thicker and thicker and thicker. So this is 1,000 microns, so this build is on the order of 4 millimeters or so. And so if you get too much coalescence of the powder, this can happen. So that's just one nice example and something to think about in these types of builds. Any questions on that? Okay. So there's, like I said, a lot of different articles on the current status and perspectives of polymer powders, how to make polymer powders. This review article just has this really nice diagram up here, these different powder-based processes. And of course, we're talking about SLS. We're going to talk about HSS in a second, or high-speed sintering, and we'll talk a little bit about binder jetting as well. But polymer powders are a really interesting thing to think about. And in comparison, this review article has this comparison table for SLS, which we've been talking about, and MJF, which is multi-jet fusion, which is a process invented by HP. We're going to talk about that when we go back to the other slides, but this is basically polymer powder plus ink, but it's not necessarily binder jetting because the ink is going to be used to high-speed sinter that polymer powder. So in essence, multi-jet fusion is a subset of high-speed sintering, as we'll talk about, but they point out this surface roughness measurement right here. And I think last time we talked about surface roughness, and it turns out that there's quantitative metrics for surface roughness and quantitative ways to measure surface roughness. And surface roughness really matters in metal SLS. So if you're familiar with powder bed fusion of metals, getting nice surface roughness is important because that creates mechanical stress concentrations in your part, and that has the surface of the metal has a big influence on the defects and crack propagation and how that metal fails. But surface finish is also important just for quality, for customer acceptance, for selling parts. And so This paper right here describes how to measure surface roughness using this one technique. So this might be using a stylus profilometer, just like a record player. So the needle on the record player is measuring the topology or the roughness of the sample, and then that roughness can be turned into a quantitative number, and you can read about that if you want to. But what they were looking at in this paper is just material extrusion AM parts at different profiles, whether they're scratching along the zero direction or with the roads, or whether they're scratching across the roads or scratching at 45. And this is sort of a routine part and a routine way to measure surface roughness. But there's a lot of interesting sophisticated ways to measure surface roughness, like this optical profilometer, or there's also laser scanning profilometers. Sometimes they're called white light interferometers. But basically what they all do is that they take a roughness profile, something like this, and they do quantitative evaluation of surface roughness. And it's usually expressed as something like an RMS, a root mean squared roughness. And it'll be something like 5 microns or 100 microns. So it's akin to an average feature size of these peaks. And of course, RMS is a mathematical equation. And so once you have one of these roughness profiles, you can calculate the RMS roughness. So an RMS roughness of 1 micron is pretty smooth. And RMS roughness of a silicon wafer that's basically a mirror finish is on the order of a couple nanometers, whereas the RMS roughness of something like you know, an SLS surface will be 50 microns or 100 microns or something like that. So you can see the dullness of the surface finish just from the scattering, or the RMS roughness of, say, a piece of printer paper is on the order of 20 microns or something like that. And so the RMS surface roughness gives you an idea of the surface quality. And of course, different printing techniques, whether it's powder-based or whether it's liquid-based or something else, will have different surface roughnesses. And so that will matter as you start to think about what process you're going to use, coupled to what material you're interested in and what application your product's going to be used in. So that's just a quick aside on surface roughness, because it was part of that review paper. I thought I would bring it up. But if you're interested in quantitative surface roughness measurements, there's ways to do that. There's even ways to do that at Penn State, because we have these laser scanning profilometers or white light interferometers. Now, the other thing that we didn't talk about too much is just powder sieving, but that's pretty easy to think about. So this is just with different size screens. So these screens are like window screens, although they're called meshes sometimes. So this is nothing really sophisticated here. It's just you take a different size window screen, you sieve through the powder, and the big particles are left on top, and the small particles that are fit through that mesh, and the smaller ones end up in the bottom, and then you're able to separate powder based on its size like that. And so the typical size range produced in industry is on the order of 200 microns to 50 microns. And this is just a news article from America Makes on these different types of powder sieving stations. You know, you can imagine if you have to sieve 100 pounds of powder or 500 pounds of powder, this gets to be a tricky operation where you have all this powder flying around. And so they've got different ways to sieve this powder and get rid of the particles that they don't want. What's especially important is recycling polymer powder. And so in order to recycle powder, you may have pieces of powder that aren't necessarily sintered onto the part, but still end up in the bed, because you get this phenomenon called splatter from the laser. So when you're shining a laser very quickly across the surface of this powder, you can have some powder that's ejected, or you can have some powder just right on the edge that's sort of sintered off to the side. And so getting rid of these splatter particles that are sort of fused but not part of the part is important in order to be able to reuse the powder. And so the powder will age, the powder will slowly coalesce because you're heating it up to high temperature in the bed anyway. And so being able to reuse these powders, oftentimes they're sieved after they go through the SLS process in order to make sure the powder is all broken up and ready to go. So one of the important jobs of this sieving process is to get rid of any unusual shaped powder as it's passed through the instrument, because of course these larger particles will lead to spreading defects, streaking in the powder bed, other sorts of undesirable things. Any questions on that? So another important aspect of producing usable polymer powders in SLS is anti-static agents and also flow agents. And so there's this nice article here about the use of these things. So these are added in low percentages to polymer powders. And so you know that solid polymers that you buy from Sabic or Dow Chemical or ExxonMobil, they will also have extrusion processing aids or plasticizers or antioxidants. It turns out there's lots of things in that reel of colorants, in that reel of PLA that you buy. And so this is just a nice study showing that they're going to add 0.1% of this aerosol R8200. So this is a flow agent. And basically this helps polymer powder flow better. That's why it's called a flow agent. And so you can see the flow time for a certain measurement they're going to make goes way down, which means that this will flow more easily. And also this bulk density goes up. And so if the polymer is flowing more easily, the bulk density increases. And so that can help with sintering. And so when they looked at the before and after, you can see that there's more defects in sintered part with no flow agent. Now, that's not to say that there's no defects in once you put the flow agent in there. You get rid of some defects, you get a more consolidated part, so you can get better consolidation. with flow agent. That doesn't mean to say that there's no defects in the part on the bottom, but it's a lot less. And so these sorts of things are added into commercial formulations of powders. And this is really what's in those bottles that we saw before from a supplier. There's flow agents in there, there's colorants, there's other things that are used to make these industrial powders work correctly. So, and this is just one example. So any questions so far? I'll pause here. People can unmute themselves and ask questions or clarifications or anything that people want to expand on in this section. All right, we have about 25 more minutes, so we'll press ahead. So as we've discussed a few times, there just are not many production grade SLS materials out there. And I just wanted to remind you of one of the families of powdered SLS materials that you can buy. And so this is from 3D Systems. So they make metal and polymer powder bed fusion machines, and they make polystyrene, thermoplastic, nylon 12, or PA11 and PA12 base powders, and they call these Duraform powders. And so that just tells us that we have to look a little bit more into what's going on for exactly what those polymers are. They don't tell you what the zero shear viscosity is. It's nice that they tell you what the color is. So they sell both white and black and off-white material, depending on what you're interested in. But, you know, these are all variations in terms of, here's a flex material. Remember, anytime we see thermoplastic polyurethane, this will tend to be flexible. Turns out that polystyrene is amorphous. So there aren't many of those, but you can buy polystyrene powder, and this is probably for metal casting, since it's a cast form material. And so these are the different properties. And so whether you're burning out this material for investment casting or you're using it for biomedical or other things, companies are out there to help you select the right feedstock for the right application. And so in general, there aren't lots of these materials available, but there's some resources out there from the manufacturers to help you select SLS powders if you're interested in moving in that direction. There's also some papers out there on how to construct new powders or how to make composite powders. So this is a filler. And of course, this is a polymer powder. But this paper is just another example of a composite powder where they're putting in light stabilizer, lubricants, they have their filler, they have their polymer powder, and then they're making this composite powder through blending of these two powders. And so that's really interesting because the PCP powder, or this mineral filler, is a much different looking powder than the polyether sulfone powder. And so that's really interesting because now you have two really different shapes of powder, and now you can see the different powder morphology where you have the polyether sulfone pellets versus, I guess the PCP is some sort of cellulosic material where you're trying to make a biocomposite or a cellulosic composite. So you have this high performance polymer, you're putting in these other microparticles of wood, and then you're doing sintering SLS of this composite powder. So if you're interested in all the things that they had to do in order to optimize the laser power, optimize the powder spreading, optimize exactly how they made parts and what some of their conclusions were, this is a paper worth checking out, and there's just a very few of these composite SLS papers out there for new SLS feedstocks. Any questions? All right, so in the last few minutes, let's go back to lecture 6.1. And now that we've talked extensively about powder bed fusion processes, because remember SLS is a subset of powder bed fusion, we're going to talk about a couple different processes that have polymer powder involved. The first one is just this aerosint technology for using different sorts of polymer powders in a powder bed. So in this case, in this, schematic, they have powder A and powder B, but now you might be able to do dual material SLS depending on how these powders are dispensed. So this is no longer a powder spreading operation. These are two drums like a Xerox machine where you have electrostatic deposition of different powders. In specific locations. And this is akin to the Xerox process. And so if you've ever used a copier machine, the copier machine has toner in it. And the way that the toner is spread on the page and then fused is it's spread on the page with an electrostatic roller. And so the toner particles are basically patterned onto the roller. The roller electrostatically deposits the polymer powder onto the page, and then there's a fusion process. That's what the light is in a Xerox machine that fuses that toner together. But a photocopied page is basically a bunch of particles that are fused together, and if you do a bunch of Xerox processing hundreds and hundreds of times, you'll get a three-dimensional object. And so this is basically just a multi-material Xerox machine in 3 dimensions. And so this company, Aerosint, has been developing this technology, and now they can get interesting things happening where perhaps they're not using expensive PEEK throughout their powder bed. So remember, this is expensive. They can use some inexpensive support powder. Or of course, as you take the next step, you can imagine fusing both of these powders just in different areas, and so you can get multi-material SLS. But this is still research or early commercial process. So you just can't go out and buy this. But this is what's coming in one type of powder SLS process. HP multi-jet fusion is already here. And so they've opened some printing factories. There are multi-jet fusion instruments around. And so we're gonna take a look at the multi-jet fusion video because it's cool. And I think I have it queued up. And then we'll talk about what multi-jet fusion is. So bear with me here. I think this is the video. Okay, of course, this is very fancy because it's HP. Oh, if I can get the video going. All right, so we'll check out this multi-jet fusion.
HP's multi-jet fusion technology produces quality, functional parts at a production speed which is up to 10 times faster than today's competing products. Unlike the slow point processes of some current technologies, HP's multi-jet fusion technology processes parts in 2 fast, area-wide passes to achieve top-speed part production. The process begins by applying a layer of material in a work area. In the opposite direction, in one continuous pass, we print fusing and detailing agents across the full working area. This pass combines the printing with the fusing energy, and the process is then completed. HP's proprietary architecture is capable of printing 30 million drops per second along every single inch of bed width, enabling extreme precision and dimensional accuracy.
Okay, so I just wanted to stop you here because what's happening is that this material in the bed, this is powder. So that white field on the bottom is just polymer powder that's spread using a powder roller, as usual. And then what HP is doing is it's laying down ink, so that's darker than the field. And this light behind the ink is sintering. It's heating up where the ink is because the ink absorbs the light, and it's sintering the polymer powder together. So it's called multi-jet fusion because there's multiple heads, like a regular inkjet printer that prints down this ink. And then the fusion part is the light part that's sintering the powder together. So that will become more obvious as we talk about it more, but I wanted to get you all oriented to where the jetting part or the ink jetting part comes in and where the fusion part comes in, but this is still in a powder bed.
Enabling extreme precision and dimensional accuracy. To produce truly functional parts, it's important to ensure that the material has been properly fused and that part edges are smooth and well-defined. To achieve part quality at speed, HP invented a multi-agent printing process. In this process, a fusing agent is applied on a material layer where the particles are meant to fuse together. A detailing agent is applied to modify fusing and create fine detail and smooth surfaces. The area is exposed to energy, and reactions between the agents and the material cause the material to selectively fuse together to form the part. The fusing process requires accurate temperature control across the entire material layer. HP Multi-Jet Fusion's closed-loop thermal control system does this by measuring temperatures at hundreds of points on the material bed. This information then determines which areas receive more energy to raise the temperature and which areas are cooled, allowing for control of thermal bleed and layer-to-layer fusing and cooling. The result is full control over mechanical properties, dimensional accuracy, and repeatability. The process is then repeated until a complete quality, truly functional part has been formed. This is how HP's proprietary area-wide processing compares with existing popular point processing technologies for building functional parts. In the time it takes these slower point processes to build 1,000 parts, HP's multi-jet fusion technology would have created several thousands of parts. Using HP's proprietary multi-agent printing, the HP multi-jet fusion technology achieves new levels of part quality at these breakthrough speeds. In 3D design and printing, a voxel represents a value on a regular grid in a three-dimensional space, like a pixel with volume. By controlling the properties of each individual voxel through agents, HP Multi-Jet Fusion can produce parts that can't be made by other methods. Taking advantage of HP's in-depth knowledge of color science, HP's 3D printers could, in the future, selectively print a different color at each volumetric pixel. A single 3D printed part could have literally millions of colors. But more than just full-color printing of functional parts, HP's multi-agent system enables a fundamentally different approach that could unlock the full potential of 3D printing. At each voxel, HP transforming agents could control surface texture, wear, and friction, enabling single parts with multiple textures or the monitoring of part performance. The transforming agents could control the translucency of each voxel, enabling the printing of lenses or sensors. We could also optimize the strength and stiffness in portions of a part and print elastic voxels in other portions of the part. The conductivity of certain voxels could also be controlled, enabling embedded electronics. HP transforming agents could also be used to enable the printing of new advanced materials or enable emulating different materials at each voxel. HP's multi-jet fusion technology could enable design and manufacturing possibilities that surpass the limits of our imagination.
Okay, so I don't know if it can surpass the limits of our imagination, because some of that is still highly speculative. But this idea of using inkjet so they talk about agents, or they talk about putting down fusing agents. It's basically an inkjet process, which of course HP is good at. And then these fusing agents allow specific locations to be fused by IR light. And so this whole idea of using different inks to transform the material or transform the elasticity or the conductivity is still yet to be demonstrated. Of course, HP is very good at color, but multi-jet fusion is out there, and there's lots of these things available. And the parts look a lot like SLS parts that they can produce so far. They just produce it in a different manner. And so this sort of shows the different processes or the different steps in the process. So remember, in essence, the material is polymer powder. So you still need good powder spreading, and you still need a good powder feedstock, just like we talked about before. In fact, usually you get PA11, PA12, there's TPU powders coming. This fusing agent is an ink from an inkjet head. So detailing agent is just on the edge to get a good unfused part, and then you have an IR lamp. So this is not really a SLS process because you don't have a laser, and you're not selectively sintering specific areas with the laser, so you're not moving the laser around. This lamp is over the whole bed. And so you have a powder preheating lamp here to get everything up to temperature. And then you have a fusing lamp, but this is over entire bed. So it's not SLS. You need these fusing agents, or you need the ink pattern in order to describe where the part is going to be fused. And so what's interesting is that HP has talked about collaborations with materials companies like Arkema. So you should know that name because they have a big R&D facility in King of Prussia. But you see Kynar here, so that's a type of PVDF. PVAX copolymers, polyamides, and others. You know, they're really trying to adopt new types of polymer powders for open materials. So new types of polymer powders, because of course HP doesn't make polymer powder itself, but HP really wants to sell you the machine and of course sell you the ink. Is there any question on this multi-jet fusion? And we'll just wind up with one or two more slides to show you where multi-jet fusion comes from, but any questions on this process in terms of why this is different than SLS, or why this is similar in terms of powder feedstock? Okay, so this multi-jet fusion, even though HP has a really nice video, and of course they're really good at describing how the inkjet process works, comes from this area called high-speed sintering, or this technology called high-speed sintering. And so high-speed sintering is an offshoot of powder processing, and it was invented at Loughborough University, and here's some links to check out. But high-speed sintering is basically full IR illumination of powder bed plus ink that defines fusion area. So we can go for lower power energy sources because the ink, or the dark parts of the powder bed where the ink is deposited, is where the fusion is going to happen. So you get no fusion of powder in uninked areas. So the ink is defining the shape, and of course that can be deposited using inkjet technology, and then you get fusion from the IR lamp. And so this is just another way to accomplish these sorts of powder-based additive processing. And of course, depending on how sophisticated the ink is, or depending on what sort of properties you want, you can modulate the mechanical properties of the base resin. In general, the properties from high-speed sintering or multi-jet fusion are similar to SLS, but of course it depends on the details of the powder you use, how much ink is there, what the conditions were, what the design of the part is, etc. But the parts that you get out of this are similar to what you get from SLS. It's just another way to accomplish the 3D building of the material. Okay, any questions on this? So that's as far as we're going to go today. I wanted to finish up as much of SLS as we could get to. We're going to talk a little bit more about these sintering processes next time, and then we're going to get on to different sorts of additive processing with polymers, not necessarily thermal processing anymore, but chemical reaction bonding. We're almost done with thermal, and we'll switch over to the other part of the ASTM diagram where we talk about chemical reactions and how to build up three-dimensional parts from those types of polymer processes. Any final questions, comments from class? All right, well, I will see you on Zoom on Tuesday. Thank you very much.